All right, guys, we're going to look at the Maclaurin expansion for f of x equals sine x. All right, so if you don't know, Maclaurin series are basically Taylor series that are centered at 0 instead of centered at some other value of c. So we're gonna be using Taylor coefficients and everything to build this series. And basically, the idea is we're trying to build some power function that's going to estimate this function within some given interval. So the very first thing to do is to find the values of f and its derivatives at x equals 0. Right. So if I start by saying, hey, look, f of x sine of x, and then let me find f of 0, right? Of course, we all know sine of 0 is 0. I can find f prime, that's just cosine x, which means f prime of 0 is 1. If I do f double prime, second derivative, I get negative sine of x, and negative sine of 0 is still 0. And when I get to the third derivative, I get negative cosine, right? So then the third derivative evaluated at 0 is simply negative 1. Now if I go on to the fourth derivative, and I'll write this out this time, I end up getting plain old sine of x. And if I evaluate that at 0, of course I get 0, right? So hopefully you're noticing that that this line right here is the same as the original, and then that's going to repeat, right? It's very cyclical, so you'll see that it'll keep happening forever. So we've got our Taylor coefficients, or at least a part of it right here, right? We need that derivative evaluated at that value, right? So so we can actually write that the sine of x is equal to, well, let's check the first one. And the first term is just plain old 0, right? And then we're going to add the first derivative evaluated at 0 over 1 factorial times x to the first, right? And we're going to add the second derivative evaluated at 0 over 2 factorial. These are the Taylor coefficients, right? Times x to the second plus, now we've got the third derivative evaluated at 0 over 3 factorial times x cubed, right? I'll put one more in here, right? We did all the way up to the fourth, so we'll do we'll do the fourth derivative evaluated at 0 over 4 factorial times x to the fourth, and then of course keeps going forever, right? So I'm gonna rewrite that just by kind of cleaning them up a little bit. So this is 0, right? F evaluated at 0 is 0. F prime of 0 is 1 over 1 factorial times x. And I'm going to stop writing extra stuff like that, right? We know that's just 1. Second derivative, that's simply 0 over 2 factorial times x squared, right? And then we've got negative 1 over 3 factorial times x cubed. And what I'm doing is I'm just I'm filling in these coefficients, right? So that's 0 over 4 factorial times x to the fourth. And then I'm going to continue the pattern a little bit further, right? We kind of know what's going to happen here. So this would be 1 over 5 factorial x to the fifth. We'd have 0 x to the sixth over 6 factorial. And then I'm going to change the plus and negative to a minus. So negative x to the seventh over 7 factorial. And it's going to go on forever, right? And hopefully you're noticing that that is 0, 0, 0, 0. And look, I mean, all the evens cancel out, right? So right now, cleaning all of this up, I've got that the sine of x is equal to x minus x cubed over 3 factorial plus, that's that one, right? X to the fifth over 5 factorial. What happens to the seventh? Now it's minus, right? over 7 factorial. And that's going to go forever. Positive term, negative term, positive term, negative term. And look at the exponents and the factorial, right? They actually increase by one odd number every time. So if I'm going to try to write this out, we've got an alternating series. I'm going to write it out in summation notation. We're going to go from 0 to infinity. I'll put my alternator here in front, negative 1 to the k. And it's going to be x to the, well, let's think. An odd number is always one more than an even, right? So we'll do 2k plus 1 as our exponent. And then, of course, if that's our exponent, that should be our factorial as well underneath. And we can always double check, which we absolutely should, right? We should make sure that what we get for our expression here, if I plug in 0, I can actually get the right thing, right? So that's going to be, my first term is positive. That's x to the first over 1 factorial. That works. I'll try 1. I put in 1. I get a negative term for my second. Perfect. 2 times 1 is 2. That's 3. Perfect. So everything checks out here. So we've written our sine function. Here's our Maclaurin expansion for sine function. We've got a series. Of course, we have a test for alternating series to see if it converges or diverges. We can apply that. And then eventually we're going to work with error bounds on this. What your exercise is now is to try to write the Maclaurin expansion for the cosine of x. Cosine of x. Good luck, guys.